All right, guys. So I wanted to go through a couple of the highlights from the reading in the Trotex on acid-base neutralization reactions. So this is the second type of aqueous solution reaction that we're going to be studying, and it's a big one. It's going to come up now, and we're going to kind of be introduced to just the basics of acid-base neutralization. But then when third quarter comes along, we're going to do a whole chapter dealing with just acid-base chemistry. So this is a very important type of reaction, and it's it's going to come up a lot in this course. So let's go ahead and get started. One of the things I wanted to do is I wanted to work through a very typical problem from an acid-base neutralization reaction, and that's a titration problem. So I've typed one up here involving acetic acid, and then that's being titrated with sodium hydroxide and to be neutralized. So to go through the kind of the basics of the titration reaction, in a titration reaction, what we'll have we're going to have two main things. We're going to have usually in a burette. So a burette, has a long tube. It's got all these volume marks on it. Okay. And then it's going to have a valve called a stopcock. And then, it's got a little, being held in a ring stand. And you can deliver this liquid into a beaker. Now, in the beaker, what we'll have is our unknown solution. Okay, so very often we'll have an acid in one and a base in the other, or vice versa. So in this case, what we're going to have is we're going to have 45 milliliters of this acetic acid solution. Oh. COOH. All right, so we're going to have 45 milliliters of the acetic acid solution. I can erase that. And then here, we're going to have the sodium hydroxide solution. And the idea with titration is that we will use the stoichiometry of a neutralization reaction in order to determine an unknown concentration. So we want to know what the concentration of this liquid is right there. We know its volume. We know it's acetic acid. We don't know what the concentration of acetic acid is. What we do know is that we have a sodium hydroxide solution, and we know its concentration very well. So the thing that we are titrating with will know its concentration very well. So in this case, I made up this number, it's 0.1467 molar. That's being delivered there. So we know the volume that it's going to take to neutralize, and later on we'll get into how we know it's neutralized. We'll use a pH indicator, or we'll use like a pH meter to look at the titration. But we're going to know when it's neutralized. It's a very specific point, and we're going to know the volume. So in this case, and actually I probably should use more sig figs. Let's just say that's 15.00 milliliters. Okay, so burettes, they can measure volumes out to the hundredth of a milliliter. And so we're going to know very precisely how much sodium hydroxide that we added. So the first thing we have to do when we do a titration problem is we have to look at the stoichiometry. And this one's going to be fairly straightforward. We're going to have the acetic acid, and that's going to react with the sodium hydroxide in a nice 1-to-1 ratio. It's supposed to be an AQ. And it's going to be a nice 1-to-1 ratio, and it's going to form water, and it's going to form aqueous sodium acetate. And because this is COO, because this is has a sodium ion and also an acetate, it's going to be soluble. So that's not going to there's not going to be solid forming from this. So this is a nice 1-to-1 ratio. And if you look at the net ionic equation, you can see even better. So CH3COH, so that's acetic acid. And then hydroxide is going to react with that to form water plus an acetate ion, CO minus. Okay, so this is the net ionic equation. And this is what acid-base neutralization is. It's it's very much like a precipitation reaction, that it's a double replacement. So we have this positive ion, this H plus right there, and that positive sodium, and they just kind of switch partners. and they're going to form water, plus a salt. So we have the stoichiometry now, and so the logic behind this problem is we're going to find how many moles of hydroxide was added. Okay, and so to do that, we're going to use the volume that we added. So we're going to add 0.01500 liters of sodium hydroxide. We know that every liter has 0.1467 moles of hydroxide in it. And what that will give us is 2.20 times 10 to the minus 3 moles of hydroxide. Now, forward there. All right, so we have that many moles of hydroxide that we've added. Now, what we know from up here, once again, is that for every mole of hydroxide that I add, it's going to neutralize 1 mole of the ammonium acetate. And so, using the stoichiometry of that problem, what I'll say is 2.20 times 10 to the minus 3 moles of hydroxide, and then 1 mole of hydroxide will neutralize 1 mole of acetic acid. And so that means I would have had 2.20 times 10 to the minus 3 moles of acetic acid in the original. So in this 45 milliliters. Now, you may look at this like, wow, that's overkill, Dr. Melly. I could tell after you calculate it right here how many moles of acetic acid were in there because this 1-to-1 ratio. But just a warning, there won't always be a 1-to-1 ratio. If this was, say, sulfuric acid, it would have 2 hydrogens. And so there would be, like, for 1 mole of sulfuric acid, we require 2 moles of hydroxide. And then you'd have to adjust for that in the stoichiometry. So, always keep that in mind. Always keep the stoichiometry of the neutralization reaction in mind. But finally, the question is, what's the concentration of acetic acid? Well, now we can find that because concentration is moles per liter. And we know that we have 2.20 times 10 to the minus 3 moles of acetic acid. Originally, before it was neutralized, that's how much we had. And then that was in a volume of 0.045 liters. And so that gives us a final concentration of 0.0489 molar. Okay, so at the end, once we know how many moles of acid we had, we just divide by the original volume, and that gives us our concentration. So this is the basis behind any titration you do. Is we'll use the solution of whose concentration we know. We'll measure the volume it takes to neutralize. In the case of acid-base titrations, to neutralize the other solution, and then we'll relate moles of what we add to moles of what was in the original solution, and then divide by the volume and get our unknown concentration. The other thing I wanted to quickly mention is kind of reiterate again these notable acid-base reactions, and there's 2 reactions that really kind of come up often that I want to make sure you guys know about, and these are reactions that involve gas. So one is the reaction with a carbonate. And so what you'll see, and I'm not going to do the whole, balanced reaction thing. I just want you to see the reactants and the products of these. But if I have any solid carbonate, so sodium carbonate, I have solid sodium carbonate, and then I add, say, aqueous hydrochloric acid, and I add it to that. What we're going to make from that is we're going to make carbon dioxide gas. So you're going to start, this is a gas evolving reaction. It's going to evolve carbon dioxide. You will also have water, being made, and then, we'll have sodium chloride left as well. Okay? So these are what carbonates do, and bicarbonates will do the same thing. HCO3, I'm going to make this one aqueous. It doesn't really matter if it's solid or aqueous. If I add HCl or any acid to that, the same thing is going to happen. I'm going to make CO2 gas. I'm going to make H2O. And then I'll have the the salt. So again, these are obviously they're not balanced, but I want you to notice this whole CO2 and H2O. Okay, when we add an acid to a carbonate, this is a reaction that you guys should be familiar with. The other thing that can come up occasionally, not as much as the carbonates, is when you add it to a sulfide. So say that you had, I'm tired of sodium, let's do potassium. So say that you had potassium sulfide and you had a solution of potassium sulfide, and then you acidified it, okay, you used HCl. If you're not careful, what will happen here is you will make hydrogen sulfide gas. Okay, so hydrogen sulfide gas is going to be bubbled off, and then KCl will be aqueous. This is poisonous. Okay, it smells like rotten eggs, and so it's one of those things. A little knowledge is a dangerous thing. If you add it unintentionally, if you were to add an acid to a sulfide solution, it would evolve this hydrogen sulfide gas, and you have to be careful with it. You have to do it in a hood. It does smell bad, and too much hydrogen sulfide could cause you to suffocate. Okay, so anyway, these are two gas evolving reactions. I want you to know they are acid-base neutralizations. Notice that the hydrogen, in this case, and the sulfide join up, so we still have the still replacement. The hydrogen does join up with the carbonate. And actually, there's kind of like an intermediate step where we form what's called carbonic acid, but carbonic acid falls apart into carbon dioxide and water. Okay, so this is still a double replacement. It just kind of gets hidden a little bit in the case of the carbonate. All right, so those are the two things I wanted to show you. Again, the rest of the information you can get from your textbook, and let me know if you guys have any questions.